First of all, we'll learn how division is done. When we divide 5 by 3, what we get is 5 divided by 3. 3 ones are 3 minus we are left with 2. So this 5 that we divide, the main number is called the dividend. And this one is called the divisor. The number that we divide with is called the divisor. The number that we multiply with, which we are dividing by, this is called the quotient. And the final, after subtraction, the number that we get is called the remainder. Remember, remainder is always less than divisor and can be minimum 0. It must be positive or it can also be 0, but should always be less than divisor, because 3 ones are 3, 5 minus 3, you'll always get a number that is less than the divisor. Okay, from this we can make out that dividend is equals to divisor into quotient plus remainder. This is our division algorithm. Dividend equals to divisor into quotient plus remainder. Dividend 5 equals to 3 into 1 plus 2. 3 into 1 is 3 plus 2 is 5. So 5 equals to 5. So this is our division algorithm. So we know how to find the HCF of a number using division method. Let's recall it by solving one example. Find the HCF of 4052 and 12576 using division method. So solution, what we do is we take the bigger number as the dividend 12576 and we divide by the smaller number 4052. On dividing this, say we multiply with 3, we multiply with such a number that on subtracting, the number remainder that we get should be less than the divisor. Remainder should always be less than divisor. So on 3, when we multiply, 3 to 6, 5 3 15, 4 3 12. Now what happens is this remainder that we get becomes the divisor and the previous divisor becomes the dividend. This is the step that we follow while finding HCF using division method. So 420 into 9, 900, 9 to 18, we have 1 in hand, 9 4 36 plus 1 37. So on subtraction, 2, 4 gives 1 over here becomes 3, 10 gives 1 to the next one becomes 9, 15 minus 8 7, 9 minus 7 2, 3 minus 3 0. Now 420 comes here. 272 into 1 is 272. Similarly, this became our new divisor and the previous divisor becomes the dividend. So 1s are 272. So 1, 10 minus 2, 8, 4, 3. This becomes 11. 11 minus 7 is 4. 3 minus 2, 1. We have 148. Now this remainder becomes the new divisor and the previous divisor becomes the dividend. 272, 148 ones are 148. Subtraction, we get 6. 12 minus 8 is 4. 6 minus 4, 2. 124. 148. 124, 1. 124. Subtraction, we get 24. We have 124. 24 into 5 is 120. We have 4 left, then we have 24. 4, 6, 24. Subtraction, we get 0 as the remainder. So the last divisor that we have, this becomes our HCF. So therefore, HCF of 4052, 12576 is equals to 4. This is how we find the HCF using division method. Now coming to the main point, that is our Euclid's division lemma. So what this theorem states is that given two positive integers a and b, there exists unique integers q and r. Q basically denoting the quotient and r basically denoting the remainder, satisfying a equals to bq, where a is our dividend, b becomes our divisor, q becomes the quotient, plus r, where r is the remainder, and r should be less than b. The remainder is always less than the divisor, and the remainder should be greater than or equal to 0. The minimum value of the remainder can be 0, and maximum it can be just below the divisor. It cannot be equal to the divisor. That's why only less than sign, not less than and equal to. Only less than sign. So this is our Euclid's division lemma. Now let's see how we solve the example using, this was just an example. This type of question you won't be asked by using division method. You will be asked to solve the HCF using Euclid's division lemma. So use Euclid's division lemma or algorithm to find the HCF of 4052 and 12576. Okay. So what we did over here in the division method, we are going to do the exact same process, but we'll be representing in this different manner. So now, since 12576 is greater than 4052, we apply division lemma and get 12576, the dividend equals to divisor into quotient plus the remainder, that is 420. You can even multiply and check. When you multiply with 3 and add this, you get back this number. So this is our first step. Now the remainder, as we see, is not equals to 0. We'll continue this steps till the remainder becomes 0. Since the remainder is not 0, since the remainder 420 is there and which is not equals to 0, we apply the division lemma to 4052 and 420 to get. Now in the next step, what we did was we took 4052 as a dividend. 4052 becomes our dividend, equals to our divisor is 420 into the quotient is 9 plus the remainder is 272. Again you can check the remainder is less than the divisor and also remainder is not equals to 0, so we need to continue this process. we consider the new divisor So we are considering the new divisor as 272 new divisor is 420. We are taking the numbers divisor, that is 420, and the remainder (272) and apply the division lemma. To get, so now this becomes our dividend, the remainder becomes our divisor. So 272 into 1 was 272 plus 148. Again, in the same way, we consider the new divisor, (272) and the new remainder. In every step, we'll be taking the divisor and the remainder. Here divisor is 272 and remainder is 148. So we consider the new divisor 272 and the new remainder 148 and applying division lemma. To get 272, this becomes our new dividend, equals to 148 into 1 plus 124. Now what will happen is 148, the new divisor, this divisor will consider, and another number we'll consider is the new remainder. So we consider the new divisor here is 148 and the new remainder is 124 and applying division lemma. We get 148 is equals to 124 into 1 plus 24. 148 equals to 124 into 1 plus 24. Again the same process we consider. We'll continue this process till the remainder becomes 0. So we consider the new divisor, that is 124, and the new remainder, that is 24, and applying division lemma. We get 124 equals to 24 into 5 is 120 plus 4 is 124. Again the remainder is not 0, so we'll again consider this divisor and this remainder. We consider the new divisor, that is 24, and the new remainder, four, and applying division lemma, we get 24 equals to 4 into 6, 6 4s are 24 plus 0. So what is our last divisor? 4. So the remainder has now become 0. So our procedure stops. Since the divisor, at the last step, whatever the divisor is, that becomes our HCF. Since the divisor at this stage is 4, the HCF of 4052 and 12,576 is 4. This is how we'll be writing in case of Euclid's algorithm, when you are asked to find the HCF in case of Euclid's algorithm. We are basically doing the division method, but we are writing in terms of words. Okay. So this is the first type of question that you will be getting from Euclid's division lemma. The other type of question that you may get is number 2. Show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Okay, this type of questions will be very much focusing on the language that we'll be writing in. At the same time, we'll also need to understand what we are writing. So in the solution, we have, let a be any positive integer and b equals to 2. See, what was given in Euclid's division, that we need to consider two positive integers a and b. You can take other alphabets as well. We took a and b itself, and b was our divisor. A equals to b into q plus this one. So we need to show the integers in form of 2q or 2q plus 1. So we took the divisor, this b equals to 2. So after taking b equals to 2, so then by Euclid's algorithm, a will be equals to 2q plus r. A equals to bq plus r, so a equals to 2q plus r for some integer q that is greater than 0, and r will be equals to 0 or r will be equals to 1, because the remainder should be less than the divisor. So less than 2 we have either 0 or 1. Since we are considering integers and it cannot be negative, so it should be 0 or it can be 1. Why? Because the remainder is less than the divisor 2 and greater than equals to 0. So it can be 0, it can be 1. We cannot take 2 because r is less than 2. It cannot be equal to 2. Okay. So from here, what we get is either a equals to 2q. If you put r as 0, then we get a equals to 2q, or we get 2q plus 1 if you put r equals to 1. So all integers are either of the form 2q or 2q plus 1. So if a is of the form 2q, then a is an even integer. Also, a positive integer can be either even or odd. Therefore, now if the even integers is of the form 2q, if a is of the form 2q, then it is an even integer. Then if it becomes 2q plus 1, then it will become odd. Therefore, any positive odd integer is of the form 2q plus 1. A simple reason also to this is 2 into q is any even integer. 2 into q, you take any integer, if you multiply with 2, it becomes even. Say you took q as 5, so 5 into 2 is 10. Now to any even integer, if you add 1, then it will automatically become odd. That is why 2q plus 1 denotes any positive odd integer. The last example show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Solution. So first of all, like we began here, we will take two integers. So let a be any positive integer and in this case, as we needed to show in forms of 2q and 2q plus 1, we took b as 2 because 2 into q was there. Now here we have 4 into q, therefore we'll take b as 4. Then by Euclid's algorithm, what happens is a equals to 4q plus r where r is equals to 0, 1, 2, 3 because r is less than the divisor, r should be less than divisor and greater than equals to 0. So it can be 0, it can be 1, 2, 3, it cannot be 4 because r is less than 4. That is, a can be 4q plus 1 or 4q plus 1 or 4q plus 2 or 4q plus 3, where q is the quotient. However, we need to show that q plus 1 and 4q plus 3 as positive odd integers. So we'll remove whatever that is even over here. However, since a is odd, a cannot be 4q or 4q plus 2, since they are both divisible by 2. Therefore, any odd integer is of the form 4q plus 1, or it is of the form 4q plus 3. So this is how you proceed and you come to conclusion in Euclid's division lemma. With this we come to the end of this lecture. Please practice exercise 1.1 from your textbook.